are going to talk about some relationships between chords, secants, and tangents in a circle. So there'll be a little more equation-based than what you maybe saw on some of the definition-based problems. So the first relationship that we're looking at here is this idea that if you have two chords in a circle that are congruent to each other, they're going to cut off arcs that are also congruent. So I'm going to write the wording of this, and then I'll kind of like talk through the general sense of it. So in the same circle, or congruent circles, and again, this is an if and only if, which means this statement and its converse are both true. But if you have two minor arcs are going to be congruent, if and only if. Their corresponding chords are also congruent. And so basically this is what it's saying. It's saying that in a circle or congruent circles, arcs cut off by congruent chords are congruent. Okay, so here if we see that if AB is congruent to CD, then we know that arc AB and arc CD are the same. Okay, and the converse is true. If arc AB and CD are equal, then we know that the chords AB and CD would have to have the same length as well. So see if you can apply that property directly to this question on your own before I go through it. I think the wording of it is enough that should make intuitive sense for that problem. So when we look at what this problem is saying, if AC is equal to 11 and FH is equal to 11, that's telling us that these are congruent circles. Okay? So in a pair of congruent circles, congruent chords are going to cut off equal angle or equal arc measures. So here, if we see that the B to D is 1 tick mark plus another 2, E to G is 1 tick mark plus another 2, we know that those are congruent segment or congruent chords. So what that means is they're going to cut off equal arcs. So the arc from B to D and the arc from E to G are the same. If we're finding the arc E to G, what we know is that this is equivalent to the whole 360 minus the two parts 102 and 111. And so we can enter our answer as a calculation. And if we actually do the calculation here, or if we did it on the answer entry and typed it out, we would see that the solution will be 147. Okay, so either the calculated answer or the calculation will work, but it's based on the property that if arcs that are cut off by congruent chords are going to be congruent themselves. All right, second relationship that you're going to see in this section has to do with a diameter of a circle intersecting a chord at a perpendicular. And so here's what that, I'll write the wording, and then again I'll kind of write it in a little bit more plain words. If the diameter of a circle is perpendicular to a chord, then the diameter is going to bisect the chord and its arc. Okay, and so again, basically what this is saying is that the diameter perpendicular to a chord is going to bisect both that chord and its arc. Okay, so here, if EG is perpendicular to FD, so this is a diameter perpendicular to the chord, it's going to bisect that chord. So that means that FH is equal to HD. Okay, and it's going to bisect the arc and set those equal. So the measure of arc FG is also equal to the measure of arc GD. And so those are the relationships that hold true if a diameter is perpendicular to a chord. Okay, so once again, see if you can just use the relationship given and find what would the solution to this question be. Can you find JH, or the arc measure JH and the arc measure JK? Right, so in this particular case, what we see is that JL is a chord that passes through the center of that circle M. Right? And so we know that it's a diameter. That diameter intersects and is perpendicular to chord HK. So that means it bisects this chord, which doesn't necessarily come into play in this problem. It also bisects this arc, which means that the measure of JH and the measure of arc JK are equal. And so if we set their expressions equal, 3x is equal to 44 plus x, we can then solve. We get 2x is equal to 44, or x equals 22. Now, this is a multi-step question because it's not asking you to find what x is, it's asking you to evaluate. Arc JH is 3 times x, so 3 times 22 is 66. Now, we don't need to do any other calculations here. We know, based on this property, that these two arcs are the same, so that means that JK is also going to have to be 66. But if we want to confirm and make sure that we have the right answer, if we plug in 22 to this second expression, 44 plus x, we can confirm that, yes, indeed, that is 66. It's what we expected, and that will give you some confirmation that you have the right answer. All right, the next relationship is the converse of this. So it's stating the same thing, but flipping the conclusion and the hypothesis. So this is saying if a chord of a circle is the perpendicular bisector of another chord, then that first chord is going to be a diameter. Okay, so any chord that's a perpendicular bisector of another chord, okay, is also a diameter. Okay, again, that's basically what it's saying. All right. So see if you can find the solution to this next, or this question here, based on the properties that we've discussed so far. So this is a little bit more similar to the previous, not this converse, but the previous one. You have a diameter you see. AB is a chord that passes through point F. Therefore, you also see it's perpendicular to the given chord CD. That means that it bisects this chord and this arc. Well, if we know that the chord length CD is 34, that means CE and ED both have to be what? Half of 34, okay, or 17. So you can calculate that or write your answer as the calculation, but it's based on the fact that a diameter perpendicular to any chord bisects that chord. All right, the final relationship involving chords of a circle that you guys are going to be responsible for is that if you have two chords that are congruent, then that means that they're the same distance from the center of the circle. Okay, so again, I'll write the wording for it. In the same or congruent circles, if you have two chords, they will be congruent if and only if. So again, both the statement and its converse are true here if they are equidistant from the center. So once again, what this basically is stating is that congruent chords of the same circle or congruent circles, okay, are equidistant from the center of the circle. All right, so once again, see if you can apply this rule into the problem that they give you and come up with PG and PJ for this calculation, please. So again, we're told here that AC and FD are equal lengths. So here we have two chords that are the same length. This means that they're equidistant from the center. That means that this distance from P to G, that is a distance, right? The perpendicular from a chord to the center is the distance. And then this PJ is the distance from FD to the center. So those have to be equal. So we know that PG and PJ are equal to each other. And so if we set their expressions equal, x plus 57 is equivalent to 12x minus 9. And we can solve, move the x's to one side, the constants to the other. We get 66 is equal to 11x. Again, a nice, easy calculation. X is equal to 6. This is multi-step, so we're not just finding x. We want to find expressions. PG is x plus 57, so 6 plus 57. That gives us our total answer of 63. And because we know that PG and PJ have to be equal, we could just answer PJ is also 63. But since you have an expression, you can test it and you can verify your answer, because 12 times 6 minus 9 also should be 63. If we took 12 times 6 minus 9, we confirm that yes, indeed, it is 63. And so we can confirm that we have the correct answer here. All right, so that is the material from 10.3 talking about the relationship of chords in a circle. Okay, the last set of relationships that we're going to look at here, we're jumping to 10.6, and it has to do with relationships between chords, secants, and tangents. Okay? And so once again, they're calculation based. Since it connected to chords a little bit, I wanted to group them together. All right. The first one is that if you have two chords that intersect in the circle, then the product of the segments cut off by each other are equal. Bless you. Or actually, I'll put equal because we're dealing with a calculation. So here, if you have these two chords intersecting, A, B, and C, D intersect, what you're seeing here is that the product of one set of chords, so AE times EB, that product, is equal to the product of the other chords segments, DE times EC. So this is the calculation relationship that exists when the chords intersect inside the circle. Okay. So once again, see if you can take just that information and identify what would be the length, in this case, of MP in order for this relationship to hold true. Once again, you can enter your answer as calculations. The more comfortable you are doing that, probably the quicker you can work through problems. And it also allows me to see that you understand how the question is set up and what the corresponding relationships are. So here, when you see that the product of these two segments, KP, which is 14, times PM, which is our unknown, so I'll write it MP, that is the same product as the other segments, 12 times 10. So LP times PN. And so what we can do here to solve for MP is just to divide by 14, and you have your answer. You can leave it as a calculation like this. If you simplified your calculation here, 2 goes into 14, 7, 2 goes into 12, 6. 6 times 10 is 60 over 7. Okay? Or you can enter it as the calculation. And if you put this into decimal form to at least 2 decimal places, you get 8.57 minimum. You can put the other decimals there too, but any of these calculation forms would work for that. All right. Next, we have this relationship here between calculations of portions of secants and portions of tangents. And there's a couple different relationships here to think about. And these are 2 examples of what the segments of secants or the segments of secants and tangents would look like here. And notice on this first one, you have this tangent segment, and you have this secant segment, right? A tangent intersects at exactly 1 point, A. A secant intersects at 2 points, C and D here. Okay, so the first thing is looking at this product here. If a tangent and a secant intersect, they intersect so that the relationship that AB squared is equal to the exterior portion of the secant, which is BC, times the whole secant, which is BD, this whole length here. Okay, so that's a tangent secant, or the tangent segment times the secant. Okay, the second equation is if you have 2 secants. If you're multiplying 2 secants together, like this, where you have a secant segment and another secant segment, when this is the case, if you have 2 secants intersecting, then the way that you set that up is that you get the external part of the secant, EA, times the whole secant, EB, and that's equal to the other parts as well. So EC, the external piece, times the whole thing, E to D. So these are the 2 relationships that you're going to see here in the 10.6, along with the intersecting chords. And so see if you can apply one of those to this first question, please. So there may be several different forms that you might see of these same kind of things where the variable might be different parts. It might be the whole secant segment, it might be the exterior part of the secant, or it might even be like this one, the interior part. But regardless of how or where that fits, you just need to set up this relationship. So what we have right here is we have 2 secants intersecting, so this is the relationship. And we know that the exterior part, 7, times this whole measure, 7 plus 17, and that is equivalent to the exterior part, 8, times this whole measure, which is 8 plus x. So the first thing is just to set up the relationship. And once you set up the relationship, you can then solve the resulting equation. So here, 7 times 24 is equal to 8 times 8 plus x. Now, there's a couple different ways students would solve this. More than likely, if you guys went through this step right here, you probably multiplied 7 by 24, and then you distributed the 8 through and then tried to combine all your like terms. Okay? Oftentimes, like working with factors can make things easier. So if I divide both sides by 8 right here, what I see is that 8 goes into 24, leaving 3, and this gives me a smaller and easier to use number that I can do mental calculations with. So here I can just take 7 times 3, which is 21, is equal to 8 plus x. Subtract 8 from both sides, and I get my answer to be 13. And I didn't need to use a calculator to do it. Okay, so if you can see that and work with factors, sometimes it winds up being easier to find. Okay, the question asked me to find what the x was, not the whole length AC, and so I have my answer 13. Right, so you can see here the relationship is that when you have a tangent segment and a secant, right, and you can set up the relationship that the tangent segment squared is equal to the exterior portion of the secant, which in this case is 6, times the entire secant segment, which is 7 plus 6, and that's going to give you your solution for this part. So if you solve for this, 6 times 13, we extract our root, and that is enough to enter your answer. You can just write the square root of 6 times 13. You can also do the calculation for that, and you would get 8.83 approximately if you're rounding to at least 2 decimals. So either of these would be acceptable forms.